Yes, class. Good evening. Am I audible?
Good evening, yes, miss.
Assalamu alaikum, ma'am.
Walaikum assalam. So, Aram Maha, who is this? Muhammad? What's your name? Can you please tell me your pronunciation?
Miss Tarif.
Arif. Okay.
Yes, miss.
Okay. Waziha is there, and Abdullah, Talha, and Yusuf. All right. So, Tarif, this is your first class, no?
Yes, miss. My first class.
Okay. See, we had yesterday on Monday's class, we had started with circular motion. So let me just quickly brief you with it. And today we'll discuss with the timings of backup classes of yours also, all the students who were not present. Yes, Maha, your exams were going on.
Yes, ma'am, it just finished. Last
It's
month.
finished. Okay, so how did it go?
It was good.
All right. See, in the kinematics of circular motion, the first basic term that we had discussed was angular displacement. The way we have linear displacement, similarly, analog of linear displacement in circular motion in rotational dynamics is simply angular displacement. Whatever is the change in angular position, whatever is the change that occurs in angular position, that is known as angular displacement. Waziha, I think your mic is switched on. Now, whatever is the rate of change of angular displacement, that becomes your angular velocity. The way linear velocity was rate of change of linear displacement. Similarly, angular velocity becomes rate of change of angular displacement. So these were certain basic things that we had discussed, and I think only these two quantities we had discussed. Now we have to go into the details of uniform circular motion and non-uniform circular motion, because this part comes in detail and this will be used throughout, especially when you will do rotational dynamics. You have a chapter that is completely based on rotation. So there, these terms will not be repeated since they are covered here in this chapter 5th only. Formula, see, the way we represent with the help of the alphabet X displacement, we here represent by theta, because theta is the angle that is swept by the radius. Let's say this is the radius vector has swept this much amount of angle. So that is known as angular displacement. Amount of angle that is changing with respect to time, that is known as angular velocity. Whatever you understand, whatever you know about normal displacement, normal velocity, everything is same. It's just that the path is circular for angular velocity and for angular displacement. We didn't start with angular acceleration. Angular acceleration we'll cover today only. We'll cover it. We'll try to cover it. Yes, this was one good relation that we had seen. Linear velocity, angular velocity, and the radius. How are all these three related to each other? So linear velocity is the cross product of angular velocity as well as whatever is the radius vector's component. So these three things, and usually maximum times sine, the angle between angular velocity and radius is 90 degrees. So we write V as omega r. This much we had done. Now C class, for the class, some questions also we had done. Differentiation, the second part will only be clear when we'll have this class. First class that we'll attend, no, before having the class of friction or any other class, we'll try to cover differentiation and integration only, because I think that will be used. Friction and rest of the topics, angular projectile motion, motion in a straight line, that can be covered later on. But firstly, I think the prime importance topic is calculus, your mathematical physics only. See, in your uniform circular motion is not in very much detail, as well as uniform motion, circular motion is not tough as comparison with the non-uniform circular motion. So uniform circular motion is basic. It's easy if you pay attention and just understand the concepts of it. It is not difficult to understand. Uniform circular motion will be there. Now, see, 4 things I'll tell you. If you understand 4 things, see, acceleration will be what? Acceleration is simply rate of change of angular velocity. That we'll see. Formula is also there. Relation with linear angular acceleration is also there. That we'll see. But have it in your mind, acceleration will also be what? Similar, linear acceleration is rate of change of linear velocity. Angular acceleration will become rate of change of angular velocity. So it's very simple in comparison to this. All right. Yes, uniform circular motion. So for uniform circular motion, we had studied the fact that if, let's say, this velocity is tangential to this surface and the magnitude is 2 meters per second, then at this point the velocity is again tangential, but I'm noticing that the magnitude is still 2 meters per second. At this point also, if I take, velocity is 2 meters per second. So now, how can you say uniform circular motion exists? First thing is, you have to identify whether it's uniform circular motion, whether it's non-uniform circular motion. So how will you identify? First thing, if the magnitude of linear velocity remains constant, the magnitude of linear velocity, this remains constant. Like here, this was v is equal to 2 meters per second square. At every point where I had considered, the magnitude was 2 meters per second square only. So if you notice and encounter such case, quickly notice in your fact that this is what? This is your uniform circular motion. So magnitude of linear velocity is constant. And C class, if velocity is not changing, magnitude of velocity is not changing, then acceleration will also not be there. So it means there will not be acceleration. Just have it in your mind that acceleration will also not be there. Now, one thing can happen, direction of linear velocity can change. Like here also, you can see at this tangent is pointing towards the right hand side. This tangent is pointing downwards. If I drop another tangent over here, whose velocity is magnitude is still 2 meters per second, but the direction is pointing towards the left side. For those who don't know, linear velocity's direction is taken on the tangent of a circle. Just drop a tangent at that point, that will give you direction of linear velocity. And for angular velocity, it's along the axis of rotation. Along the axis of rotation, from where the rotation is occurring, the main axis. So second point, linear velocity has the liberty to change the direction. Direction of linear velocity can change. Same thing with the magnitude of, now coming to angular velocity. Omega represents your angular velocity. See, for angular velocity, magnitude has to be constant. If you see a case wherever in a circle you are observing the fact that magnitude of angular velocity is not changing with respect to position, with respect to time, or any other physical quantity, then you can consider it as, again, uniform circular motion. So magnitude of angular velocity, this is also constant. See, direction of angular velocity. Angular velocity's direction, yes, on Monday's class only we had seen that this is along the axis of rotation. Axis of rotation will remain fixed always. It's not the tangent, the direction will be different. So it means direction of angular velocity can also be constant. So the only quantity that changes is the direction of linear velocity. Rest all the quantities, be the direction and magnitude of angular velocity or the magnitude of linear velocity, this has to remain constant. So last thing to identify, fourth point, is angular velocity's direction is constant. Angular velocity's direction is constant. So let's go into the details. And okay, before going into this detail, I think just write down these 4 points. Then we can easily proceed with it. So, yes.
Ma'am, Is uniform circular motion equivalent to rotational motion?
Yes, rotational motion is your circular motion only. In rotational motion and circular motion, both are synonyms. It's just that physical quantities differ. Like you have linear velocities in yours whenever you're dealing with motion in a straight line, non-uniform, non-circular motion. If you use the term circular motion, if you use rotational motion, both are same. All the quantities that are valid for circular motion, you can easily use for rotational motion also. Even while I am also speaking, I'm also using the term rotational motion also. This we are dealing kinematics of circular motion right now. So this is kinematics of rotational motion as well. That is same. All right, Ira?
Yes.
So write down this class, then we'll start with this. Yes, you can join after 5 minutes. All those who have to attend their Maghrib prayer, you all can go. Done. If anybody is writing, just let me know. Otherwise, I'm proceeding further. C class, in this uniform circular motion, a major part of uniform circular motion we had completed on Monday only, that omega is equal to this relation. This was one relation, omega is theta by t, means angular displacement divided by time. This was another important relation. It's just that acceleration gets on added over here when we are dealing with this. C class, there will be two types of acceleration that you will study. Right now in uniform circular motion, we will be dealing with centripetal acceleration, but understand, two types of acceleration are there. Because two types of velocities are there, so definitely there will be two types of acceleration. The acceleration that is associated or occurs due to rate of change of linear velocity. Here, this is known as tangential acceleration. Velocity is tangential, acceleration that will arise will be also tangential. And here at the axis of rotation, you have angular velocity. So rate of change of angular velocity will give you angular acceleration. Angular acceleration we have. So tangential acceleration is there, angular acceleration is there. Apart from these two, there is one more acceleration. See, tangential acceleration and one more acceleration that is associated with rate of change of linear velocity. Angular velocity is different. Rate of change of angular velocity gives you angular acceleration. That is different. We are not talking about it. Let us just focus on acceleration that arises due to this linear velocity. So two types of accelerations are there. Tangential acceleration for linear velocity. No, let me write it separately. Rate of change of linear velocity. Linear velocity is the velocity that we've been studying in motion in a straight line. Linear velocity. One you have as tangential acceleration. Other you have as centripetal acceleration. Now the centripetal acceleration is very important. This is centripetal acceleration. See, what's the difference between tangential acceleration and centripetal acceleration? Both of them are related with linear velocities only. Tangential acceleration arises because of the direction, the change in rate of change of direction. This arises. You can notice the fact velocity is tangential. This part of velocity's component, this is getting changed because of the tangent on the circle. So this arises due to direction. And this arises due to magnitude. If magnitude changes with respect to time, it's not necessary that it changes non-uniformly. It can change uniformly. For example, for every 3 seconds, 2 meters per second is changing. So 2 divided by 3, that will give you centripetal acceleration. Understood? Centripetal acceleration is also rate of change of linear velocity, but it arises due to the consistency in the change in the magnitude of velocity with respect to time. So this is because of the magnitude. There are other differences. One difference is that this is tangential acceleration and this is because of the direction. So direction of tangential acceleration is with the velocity. If velocity is tangent, acceleration will also be tangent. If this tangent is pointing, let's say upwards, at this edge of a circle, at one edge of a circle, this tangential velocity, this is pointing somewhat upwards. Then acceleration, tangential acceleration will also point upwards. But direction of centripetal acceleration is different. We don't need to specify tangential acceleration. But remember class, centripetal acceleration is a full-fledged different topic within itself. It has formulas. Tangential velocity is normal rate of change of linear velocity. This tangential velocity is not normal rate of change of linear velocity. The acceleration that you have been studying since your chapter 3, that is exactly the same. But centripetal acceleration is different. The formula will be different because it's a different quantity. This is arising due to rate of change of the linear velocity. Though both are arising because of the same cause. Slight difference is because of direction, and this slight difference is because of magnitude. For example, if a circle is there, linear velocity will keep on changing everywhere. That will give you a direction of the tangential acceleration. But direction of centripetal acceleration, please note the direction of centripetal acceleration. It always points towards the center. It is directed towards the center of the circle along the radius. So if I want to find out direction of tangential centripetal acceleration at this point A, along the radius and pointing towards the center. Pointing towards the center like this. So direction, remember this is along the radius towards the center. And the formula is very easy. Formula for this is very easy. Acceleration, a centripetal's acceleration formula is simply v square divided by r. Centripetal acceleration formula is v square divided by r. So v is what? V is the linear velocity. This is the linear velocity. And r is radius of circle because circular motion has been covered. So r is radius of circle. Even you can do one thing. One relation we had studied yesterday, v is equal to omega r. Just keep in over here. So v square will become omega square r square divided by r. This r gets cancelled. Centripetal acceleration also becomes equal to omega square r. So just in case in your question, if linear velocity is not given, rather angular velocity is given, you can use the second formula. Both of these formula will be used a lot, even in 12 standards. For electrostatics type of lesson where there is no relation of mechanics, these kinds of relations still get used wherever there is a circular motion covered. If electron covers a circular motion around the nucleus or any type of path. So this is standardized formula for circular motion. For example, let's take a question. Let's understand with this with the help of a question. A body is moving on a circular track with a speed of 10 meter per second. Fine. Radius of the track is 2 meters. If you are asked to calculate, one is angular velocity. Angular velocity is what? Omega. Omega is that symbol. W, I write, that is omega. And second is centripetal acceleration. If this is a question given to you. So see, velocity, speed is given. You can, I think this should have been with velocity of that is better. The speed becomes completely, though even if in your question speed is given, you can use, but speed becomes a scalar quantity. So it's better if we write velocity with velocity of 10 meter per second. Now see, velocity is given to you and radius. Only two quantities are given to you. Velocity is given as 10 meter per second and radius is given as 2 meter. Yes, right? Only these two quantities are given. So which formula should we use for angular velocity? Can anybody answer? Okay, do one thing. Take 2 minutes, answer both the parts. Both the parts are very easy. Reply me in the chat box. Just take 2 minutes, try this question. Very easy formula based question. Which relation will we use for angular velocity? If we have angular velocity, how will we calculate centripetal acceleration? At least angular velocity tell me. Centripetal acceleration I'll solve. Angular velocity. Yes, class, answers? See, there was, yes, right answer. See, there was a relation we had done between V, omega, and R. What was that relation? Can anybody answer? Apart from Waziha. Waziha, just a slight mistake you have done. Yes, one relation we did which connected V, capital R, and omega. Aisha, do you remember?
V is equal to omega r.
Perfect. V is equal to omega r. So if V is equal to omega r, omega will be equal to V divided by R. See, V is 10, R is 2, this becomes 5. Understand? This is simply 5. You have angular velocity, so radian will be, SI unit will be radian per second. So this is the formula for angular velocity. So I think, Wazia, you had just inverted it. I think R by V must have done it. That's why it was 1.5. For second part we have just studied, and centripetal acceleration is V square divided by the radius. So V is square is 10 into 10, radius is 2. So that gives 50. Centripetal acceleration's unit is meter per second square. Centripetal's acceleration's unit. Oh. Noted till here, then we'll begin with non-uniform. So see class, just a very small summary of what we have done. Angular velocity, linear velocity, two types of velocities are there. Linear velocity is not a part of your circular rotational dynamics or rotational kinematics. Linear velocities, direction and magnitude both will change, whereas angular velocities, magnitude will remain constant, but and direction both will remain constant. So out of all the things that we have studied, only direction of velocity can change. Two types of acceleration will arise because of it: tangential and centripetal acceleration. When there's a rate of change of acceleration, linear velocity, both these accelerations arise. Rate of change of linear velocity gives you magnitude of tangential acceleration, whereas V square by R gives you centripetal acceleration. Remember the direction of centripetal acceleration along the radius and towards the center. These are the basic things for it. I note it down, then we'll do non-uniform. Non-uniform has much greater part because there you have to have tangential, the acceleration is also changing, centripetal's acceleration magnitude is also changing. Here most of the things were constant, so that's why this was very short. We'll do now non-uniform. If you have any doubts, you can text me in the chat column as well. I'll answer it, or you can unmute yourself and ask also. Aisha, you're asking something?
Yes, ma'am. Ma'am, in that question, we are supposed to find angular velocity, right? But that formula is for linear velocity.
This
V
formula,
is
is equal to omega. That is linear velocity. So yes, linear velocity is given to us. So linear velocity is equal to angular velocity multiplied by radius. From here we can get this. This is unknown to us. This is given. This is given.
Omega is the angle, right?
Angular velocity. Angular velocity. Angle is
Oh.
theta. Okay. Angular displacement, or the angle is theta. Here I have written this opposite. Please make a correction. I think here I have written direction and here I have written magnitude. See, tangential acceleration, this is coming because change in the magnitude of this direction is changing. Because of the tangent, we are having the direction along the center and towards the radius. So this is direction. By mistake, I had written direction here and magnitude here. Because whatever is the change in magnitude, we are dividing it by time. So this is because of magnitude. Because here direction is not changing. Tangential acceleration will be having tangential velocity's direction only. Magnitude is changing, that we are trying to find out. C class, let's start with non-uniform circular motion. All the three accelerations will be involved. Tangential acceleration will also come, centripetal acceleration will also come, as well as angular acceleration will also come. Now, how will you identify whether to use tangential acceleration, circular, which one? In uniform, it was simple because in uniform, most of the things were constant. Only one thing got changed, that was the direction of linear velocity, because it was tangential and all the tangents pointing to the circle gave the different directions. Rest of the things were constant, so the two accelerations had this definite values or magnitude. Now in case of non-uniform circular motion, how will you identify? C class. If the magnitude of linear velocity is variable, magnitude is changing, it will be same. The way we had the change in magnitude gave tangential acceleration, this time also it will give you tangential acceleration. Fine. Now, if direction of linear velocity is variable, so direction, what we had studied, since all these directions that are pointing, this direction of acceleration is towards the center, so that gives centripetal acceleration. The acceleration that will be involved will be centripetal acceleration. So linear velocity's case is over. Magnitude direction can change, tangential and centripetal can be present. Now, what if magnitude of angular velocity changes? If this is variable. This is variable in case of non-uniform circular motion. Now what will arise will be angular acceleration. And direction of, regarding the direction of angular velocity, this is always pointing towards the axis of rotation. So whether it's uniform, whether it's non-uniform, its direction is towards the axis, along the axis of rotation only. So here this quantity will only be constant. So if velocity is constant, there will be no acceleration because of this component. Is this clear? If you have this clarity in your mind, now nothing is difficult. You just have to see the formula for all these accelerations. Centripetal acceleration, I have written it in detail, so I'll not repeat it. It is same only. Regarding tangential acceleration, if we talk about tangential acceleration, so tangential acceleration arises because of rate of change of magnitude of linear velocity. So this is rate of change in magnitude of the linear velocity So the way normal acceleration is solved, rate of change of velocity, this is also solved. And direction will be tangential to the circular path. Direction will be direction along with the linear velocity direction. Because if the direction is fixed here, that's why we are focusing on the magnitude. So the direction, two things you have to remember. The SI unit of this, the SI unit will be simply meter per second square, because this is similar to what your linear acceleration was. And direction, this will be tangential. This will be tangential to circular path. This is tangential to circular path. Now see, second one was centripetal acceleration. Centripetal acceleration, I have already written over there. Direction as well as the formula for it. Formula is v square by r. Direction is along the radius and towards the center. Tangential acceleration's magnitude is dv over dt, rate of change of velocity, and direction will be tangential. Last acceleration that we have not discussed is the angular acceleration. Angular acceleration is similar pattern. See, when angular displacement got changed. We got angular velocity. Now, when this angular velocity will get changed, we'll get angular acceleration. This is denoted with this symbol alpha. So this arises due to rate of change of magnitude of angular velocity. So this is due to rate of change of magnitude of angular velocity due to angular velocity. So alpha is written as rate of change of angular velocity. So SI unit of theta angular displacement was radian. This got divided by time and gave us omega. So that became radian per second. Now this is again getting divided by time. So SI unit will become radian per second square. Understood? So SI unit is simply SI unit will be radian per second square. Now direction. Direction, I have told you, for angular velocity, it is along the axis of rotation. So it will again be along the axis of rotation. It can be inwards as well along this axis of rotation, as well as it can be outwards this axis of rotation. This can be inwards as well as along this axis of rotation, as well as it can be outwards also. In magnetics, we use this symbol. No need to remember these symbols, inwards, outwards. Just remember. This is what direction will be along the magnitude, along the axis of rotation. So all these three accelerations are there. Now let's do some numericals on at least 2 to 3 numericals. Let's do on uniform circular motion, so that this topic will be clearer. Let's say a linear velocity. Linear velocity of a body changes from 10 meter per second to 3 meter per second on a circular track. As soon as the term circular track is mentioned, you will easily identify that this is a topic from circular motion. Then it says calculate change in the velocity and secondly it says tangential acceleration. We are starting from a very easy question. Initial velocity is 10 meter per second. Final velocity is 3 meter per second. So Maha, can you tell me the change in velocity? Instead of this 10, 3, no, make it 30. If initial velocity was 10 meter per second, final velocity is 30 meter per second. What is the change in velocity? Maha? No, magnitude. Initial velocity is this. Final velocity is 20. So first part says this only. This becomes, the change in velocity will become 30 minus 10. That gives you 20 meter per second. Per second. This is velocity, no? So square will not come. Tangential acceleration is what? Tangential acceleration is simply time this divided by change in velocity divided by time. So let's say on a circular track in 10 seconds. So now we'll be able to calculate. Second part will simply be what? Just the application of this question. This is a random question that I have taken. Now from after this, we will be doing proper questions. Tangential acceleration is change in velocity by change in time. So that becomes 20 divided by 10. This gives 2 meter per second square. Fine. So this way we can use. Now I'll be asking you, let's do some question. One more question let's do, then you can note it down. Again, very, very easy question. Let's do, then one good question you can practice on your own. Second question. angular velocity of a body. This time I'm referring to angular velocity. This is not the linear velocity. So angular velocity of a body changes from 5 radian per second to 25 radian per second in 5 seconds. Calculate. First part says change in angular velocity. Second part says angular acceleration. So initial velocity, angular velocity is 5 radian per second. Final angular velocity is 25 radian per second. Tarif, can you answer this? What is the change in angular velocity?
Yes, Miss, I'll try.
How much?
No, Miss, I'm doing now.
Abdullah, can you answer? Initial velocity is 5. Final is 25. What is the change?
20, ma'am.
20. It will be 20 only. 25 minus 5 will give you 20 radian per second. So Tariq, there was nothing to solve in this. This was just the change that has to be asked. Understood?
Okay, Miss. Yes,
Okay. Now angular acceleration. So angular acceleration is simply rate of change of it. First part correct, second part is also correct. Wazia, good. So angular acceleration is alpha, rate of change of angular velocity by whatever is the time given. So that becomes 20 divided by 5. We get 4 radian per second square. Now tell me, class, before we move on to other numericals and before you write down all these things, any doubt still here? Is it clear to all of you?
Ma'am, I have doubt in the first phrase of the non-uniform circular motion where you have written if the magnitude of V is equal to variable.
This one. This one?
Yes, ma'am.
Okay, see. Magnitude of linear velocity is variable means this is the circular motion that has been covered. Now let's say a point I have taken, this A point. The magnitude of the velocity is, let's say, 3 meters per second. Fine. This is point A. I choose another point B. When I calculate the magnitude at this point, it is coming out to be 2 meters per second. At this point, again the velocity has increased back, and this is 5 meters per second. So can you see at this point A it is 3, then it decreases to 2, then it again increases to 5, then it again decreases to 3. So now the magnitude is constant or variable, Wazia?
Variable.
Variable. So acceleration that will arise because of change of this magnitude, that we call it as the tangential acceleration. Clear?
Yes, ma'am.
Oh. So all of you do one thing, note down from here, wherever you get stuck, any part that you're not able to understand, let me know, I'll repeat the part, or you can even text in the chat column.
Ma'am, can you explain the fourth point?
Direction of, see, I'll explain. This is, let's say, the circular path that has been covered. Let's say this is the axis of rotation. Fine. At the axis, one axis is there. This is your circular track. This is the whole circular part that has been covered. This is the axis of rotation. Here, the circular path is being covered here. This is the axis of rotation. Supposedly, let's say the angular velocity is pointing outward from this. This is outwards. Now, even if the linear velocity's direction is changing, even if magnitude of angular velocity is changing, direction of linear velocity is changing, magnitude is changing, where is this direction of this angular velocity pointing? It is still pointing outwards because this is at the axis of rotation. So any change in magnitude or direction of the linear velocity, or even in the change of magnitude of angular velocity, direction is still remaining outwards only. Even if you take it as down into the page, let's say inwards, let's say magnitude is changing, the circular motion is occurring, but axis of rotation is exactly pointing at the same direction. That's why no acceleration arises because of this fact. Since velocity remains constant, and if there is no change in velocity, what will be the rate of change of velocity? 0. So that's why we have no acceleration for it. Got it, Aisha?
Yes, ma'am.
See, this question says angular velocity of a body changes from 25 radian per second, no, from 5 radian per second to 25 radian per second. So initial angular velocity is 5 radian per second. Final angular velocity is 25 radian per second. Time is given as 5 seconds and the radius of the circular path is 10 meters and tangential acceleration is asked. See, okay, we didn't do this relation. No, there is one relation between tangential acceleration and angular acceleration and the radius of the path. What we can do over here is, see, tangential acceleration is change in velocity by change in time. Let us calculate change in velocity. Change in angular velocity is 25 minus 5, that gives you 20 radian per second. So change in linear velocity will be change in angular acceleration multiplied by radius. So that this gives you 20 into, what is the radius given of the path? 10. So 20 into 10, which gives you 200. 200 meter per second is the change in velocity. And time is given to you 5 seconds. So your answer becomes 40, right? So tangential acceleration will be what? Now change in velocity by change in time. Velocity we have got, this is 200, by time is 5, this is equal to 40 meter per second square. Now see class, here we could have done this question had we known the relation between angular acceleration and radius also. There's one relation, you can note down this question later. First, let us do this relation. There's a relation between the tangential and angular acceleration. Relation between tangential and angular acceleration, alpha and t. The way linear velocity was equal to angular velocity cross radius. Similarly, take the analogs. Instead of linear velocity, you will have linear acceleration, that is tangential acceleration. Angular velocity, you will have angular acceleration and radius will remain the same. So tangential acceleration is alpha cross r, and since both are perpendicular, alpha r sine 90 degree will come. Tangential acceleration is alpha into r. This formula will also be used. Fine. Now note down that question also as well as this relation. So V is equal to omega r and AT is equal to alpha r. Both these relations are important because see, everywhere this is used, not directly but indirectly for the conversions. Also for the backup class of differentiation, at least we can have one class of differentiation on Friday and one class of integration on Saturday. So your basics of calculus will be over. So on Friday, same timings, but the class duration will be of only 1 hour. In 1 hour, because for differentiation only 1 hour is needed and integration 1 hour is needed. So Friday, same timings, that will be 5 p.m. to 6 p.m. This is the KSA timings. And for people who are in India, that will be 7:30 to 8:30 p.m. This is IST. This will be the class for differentiation. So this one is the radius of the circle R. Alpha is angular acceleration, whereas AT is tangential acceleration. So as you'll write it till here, just text me done in the chat column, then I'll stop the class. We'll continue this from Monday. Tangential in this way. See, tangential, here this is alpha and R. Angular acceleration is there and the radius vector is there. Here also when we got 90 degree, we had omega and R. Magnitude of angular velocity, or even you can consider angular velocity. Angular velocity is along this axis of rotation, which is perpendicular to this plane, right? Like this. This is the axis of rotation, and radius vector is like this. So both are making an angle of 90 degree. So this way, this V is equal to omega R was 90. Now here, rate of change of angular velocity is giving you alpha. So direction is same. Alpha's direction is same as that of omega. So angle between alpha and R is also 90 degree. Because this is perpendicular to the plane of the circular, be it inwards or outwards, and radius vector is lying on the plane. That's all. Okay, class, so just keep on texting me done and then you can leave the class. All those, okay, Vasia, all those who have to take the backup, please join this class. And then we'll continue from this on Monday.